So good afternoon everybody, myself Acharya Vishvendra, and today I shall be talking about equivalent spring constant of a rod. So we have done that the concept of Young's modulus. So Young's modulus comes out to be this. From here if we calculate the extension in rod, it comes out to be FL upon AY. So if we see the variations with the different parameters, then we can say that X is proportional to the force. So graph will be a straight line. For length, graph will be straight line, inversely proportional to area. So graph will be rectangular hyperbola. And if we draw graph between y and x and y, so again it will be rectangular hyperbola. So next is the concept of breaking stress, which is the minimum stress after which a material gets broken down. So let's see on what parameters it depends. So breaking stress depends only on material and is independent of its shape and size. SI unit is Newton per meter square. Next is the minimum force after when material gets broken is called the breaking strength. So this is the force, and it depends on nature of material as well as its shape and size. Basically, breaking strength is equal to breaking stress into area. Then modulus of elasticity again depends on nature of substance and independent of its dimension. So two copper rods, if they have different length and area, will have same modulus of elasticity. But again, a thin and a thick rod of same material will have same modulus of elasticity. So next is a graph based question. So larger the angle, larger will be the elasticity, and hence more elastic will that material be. Next one, now we have a question based on a cylindrical copper rod whose radius is given and various parameters are being asked. So radius is 2 mm, length is 4 meter, Young's modulus is 2 into 10 is to the power 9 Newton per coulomb, Newton per meter square, sorry. We need to find forces given, the area, the volume, longitudinal stress, then longitudinal strain, then percentage longitudinal strain, then change in length, then equivalent spring constant, then equivalent Young's modulus in series combination, then equivalent Young's modulus in parallel combination. So let's start with the first question. So area is pi r square, you substitute the value and answer is this. Volume is pi r square L, this is equal to this. A longitudinal stress is again force by area, so it will be equal to this. Next is calculations of strain. So we know that strain is equal to stress upon y. So from here we can calculate the strain, which is comes out to be this much. Percentage strain, multiply this thing with 100, so that will be percentage strain. Then we have strain as delta L by L. So if we calculate, then it comes out to be this much. And from here we can calculate change in length as 1.66 centimeter. Then we have equivalent spring constant. So suppose there are two rods. So first is they are in series combination. So we can find the equivalent spring constant as K1 and K2. And we know in series combination equivalent spring constant is added in opposite, 1 by it follows this rule. So using this we can calculate the K equivalent. Now we have a special case if lengths are equal, areas are equal. That means we can say that if we have identical rods, then in case of identical rods we have this relation, or this 1 by y equivalent is equal to this. However, if n is 1 and L equivalent is L, then we have 4 identical rods and identical dimensions. Young's modulus is added in the same way as spring constants are added. So in this way we can find the equivalent Young's modulus. Then certainly we have parallel combinations, so these are added away in a straight way. Next to now we have 3 questions, 3 rods are given, then rods are connected in series, then in parallel, then in different combination. So in series combination they are added by following 1 by k equivalent. So substituting the values we get y equivalent as this. In parallel combination they are added simply. So that will be like this, and we are being given different combination. For example, here these two are in parallel and its combination is in series. So from these two the equivalent is 5y by 6. So in that way we can calculate. Next one, now we have a question based on a rectangle, and the question is about, we are being given a rectangle having length L, breadth V, and a force is applied as shown in the figure. We need to find area of rectangle, tangential force, graph with theta, normal force, graph with theta, the ratio. So let's start with the first question. We know that area is equal to length into breadth. So that's a simple one. Then we need to find the tangential force. So tangential force is certainly the component of this force, which is F cos theta. Third is graph of F versus theta. So we know cos theta graph is like this. It is maximum at 0 and its magnitude is minimum at 90. Next we have normal force. So normal force means perpendicular to the area, and that force is F sin theta. Then we have graph. So the graph will be that of a sine graph. So if you take the ratio of the forces, it comes out to be cot theta. So in this way you can solve your questions efficiently. Let's move on to the next question. Next one, now we have the concept of energy stored in a elastic string. So the first question is about energy density. So the energy density you can verify dimensionally. I have omitted the derivation over here. So it comes out to be half into stress into strain, the first thing. Then stress can be written as y into strain. So second thing comes out to be energy density is half y strain square. So let's see the graphical variations with different parameters. So initially, if we need to draw the graph between, if strain is assumed to be constant, then we can say that energy density is proportional to y. So graph will be a straight line. However, if Young's modulus is constant, then E proportional to strain square. That means graph of E versus strain will be a parabola turning toward E axis. So if E is toward y, the graph will turn toward y, and if E is toward x, graph will turn toward x. Next is another derivation formula. We can say that energy is stress square by 2y. So if y is constant, then G density proportional to stress square, graph will be a parabola. Then we have the concept of elastic potential energy. So that is equal to E into V. This question was about mass, and it is attached to a string of length, a certain length, and it expanded through a length small l. Then gravitation potential energy changes in GL. Half of that gets stored in terms of elastic potential energy and half gets dissipated as heat. Let's start with another question. There is a certain copper wire of a certain diameter and length, and we need to calculate certain parameters based on that. The first is breaking stress is given, force is applied, then find the first thing is the surface area of the rod, second is volume, third is longitudinal stress, fourth is longitudinal strain, next is percentage strain, then elastic energy density, then elastic potential energy, then breaking stress, breaking strength. Then if a body of mass 1000 kg is lifted using this rod, then will it break? Then breaking strength is given, radius is given, we need to find breaking strength. Then next question is body of mass is to be lifted using the rod, find minimum diameter of the rod. So let's start solving the question. So the first question was about area. So we all know that area is equal to pi r square. So it will be this. Volume is pi r square L. Substituting values, we get this result. Longitudinal stress is force by area. So we can calculate that. Strain is delta L by L. And the Young's modulus we can use over here. So the strain comes out to be 1 by 45. Then percentage strain is multiply this thing by 100. Next is energy density. So it is half into stress into strain. So substituting values, we get this. Then we have energy. So energy is energy density into volume. You can find it as equal to this. Breaking stress is given to be 10 to the power 12. Breaking stress is this into area. So in this way you can find these solutions.